All right, in this video, I'm going to explain the feasibility of a linear program. So what is a feasible linear program? A feasible linear program means that basically there exists a solution to the LP. Okay, all we are saying that the LP, the linear program, is solvable. Okay, what this mean is that all constraints can be satisfied. So it's not that some constraints are contradicting each other, which means they can never be satisfied. So a feasible LP, all it means that all constraints can be satisfied. Okay. So now let's look at some examples on how to determine whether the problem is feasible or not. So I'm going to go with the problems that we discussed in class. So first one was this: maximum of 20x plus 10y such that x greater than equals to 2, y less than equals to 5, and x comma y greater than equals to 0. So this was the problem. So in this problem, this is my objective function, right? So this is the objective function. And these are the constraints. So we have 1, 2, 3, 4 constraints, right? X greater than equals to 2, y less than equals to 5, x greater than equals to 0, and y greater than equals to 0. So to determine the feasibility of a problem, you don't need to look at the objective function. So all you need to do is look at your constraints and think about, are any constraint contradicting with each other? Okay. So now first let's think about x. Okay. So are there any constraints on x that are contradicting with each other? So in this case, we can think about like let's say a number line, which is x. So the first constraint tells you, I'm gonna just for fun. So the first constraint tells you that x needs to be greater than equals to 2. So let's say 0 is here, which means 2 is, let's say, somewhere here. So the constraint tells you that x needs to be greater than equals to 2, which means that we are somewhere in this area. Right? So x cannot be lower than 2 in a number line, which means x cannot be anywhere in this area, and x has to be somewhere in this area, right? Okay. So now what is the next constraint on x? On x, the next constraint is x is greater than equals to 0, right? So this constraint tells you that x needs to be higher than 0, right? So x needs to be somewhere in this area, right? So now if you look at these two constraints, is there any way that both the constraints can be satisfied? There is, right? Why? Because if you look at this area, this area right here is the area where both constraints are satisfied. So both constraints can be satisfied, right? And it means that this problem is feasible with respect to x. Okay. So now we have to think about, is it feasible with respect to y? If it's not feasible with respect to y, then the whole LP is infeasible. So it needs to be feasible with respect to x, and it also needs to be feasible with respect to y. So in other words, it needs to be feasible for all the decision variables. Okay. So now similar thing, let's think this is a y. Let's now think, let's go back to this color. So let's think this is y. So the first constraint tells you y has to be less than equals to 5. So again, let's think this is 0 and this is your negative, right? Where this is positive. So let's say somewhere here is y equals to 5, let's say. So this constraint tells you y needs to be less than equals to 5, right? So which means that y needs to be somewhere in this region, right? It needs to be less than equals to 5. So y needs to be somewhere in this region, all right? So the next constraint on y tells you y greater than equals to 0. So if this is 0, this constraint tells you that y needs to be beyond 0, right? So that means that y needs to be somewhere here. Okay. So now again, you look at the chart. Is there any way that both the constraints can be satisfied? There is, right? So if you look at this region right here from 0 to 5, in this region, both constraints that y less than equals to 5 and y greater than equals to 0 are satisfied, which means there exists a region where both the solutions can be satisfied with respect to y. So this problem is again feasible with respect to y. So if it's feasible with respect to x and feasible with respect to y, then we can say that this LP is feasible. Okay. So let's move on to the next example. The next example was this one. Maximum 2x plus 10y such that x is less than equals to 2, y is less than equals to 5, x comma y greater than equals to 0. So again, because we are thinking about feasibility, all I'm going to look at are the constraints. I'm going to ignore my objective function. So first, let's think about x. So again, you can start with just having x, and let's say this is 0. So let's say there is 2 somewhere here. The first constraint tells you that x needs to be less than equals to 2, which means s needs to be somewhere here, right? This constraint on x tells you that x needs to be greater than equals to 0, which means x needs to be beyond 0, so somewhere here. So is there any region that both constraints can be satisfied? There is, right? So this region is the region where both constraints are satisfied, which means there exists a region where both constraints can be satisfied, which means this problem is again feasible with respect to x. Okay, so now let's think about y. And let's say 5 is somewhere here. The first constraint on y is less than equals to 5. That means y has to be somewhere before 5, right? So this is the range of, this is the constraint of y. The second constraint on y tells you y needs to be greater than equals to 0. So again, y needs to be beyond 0, which means y needs to be somewhere here. Now you would look at this, and is there any region where both constraints are satisfied? There is, right? So this region is right here where both constraints are satisfied, which means that there exists a region where both constraints can be satisfied, which means this is feasible with respect to y. So this problem is feasible both with respect to x and y, which means this is feasible with so this problem is a feasible LP, basically. Okay. All right, so let's move on to the next example, which was this. So max 2x plus 10y such that x less than equals to 2, y less than equals to 5, x comma y greater than equals to 7. Okay, so again, we are just going to look at my constraints, nothing to do with the objective function, to determine whether it's feasible or not. So let us begin with x. I'm going to plot my x right here. This is my x, this is less than 0. And let's say here is 2. And of course, 7 is more than 2, so I'm going to put 7 somewhere here. Right? So the first constraint tells you is x needs to be less than or equals to 2, which means x needs to come before 2, right? So this should be somewhere here. Right? The other constraint tells you x needs to be greater than or equals to 7. So what does it mean? That means that x needs to be beyond 7, which means that x needs to be somewhere here. So now notice there is no way you can satisfy both the constraints, right? So there is no region where I'm crossing with the red marker as well as the green marker. So there is no way both constraints can be satisfied, which means this problem is not feasible. So or infeasible with respect to x. And if it's infeasible with respect to one of the variables, then it is infeasible. So this LP is infeasible. So there is no solution to this linear program. Okay, so the other two problems that we did in the class, those were really simple, but just for completeness, I'm gonna do those as well. So max of, I think, 2x plus 10y such that xy less than or equals to 0. Now again, I'm only going to look at my constraints. So this constraint means x is less than or equals to 0. So x has to be somewhere in this region. So there are no more constraints on x, which means that there is no way that this constraint cannot be satisfied, right? So you can always find x which is lower than 0. Any negative number will be a possible solution for x. So this problem is feasible with respect to x. And similarly with respect to y is less than or equals to 0, right? So it means that it's just somewhere before 0, and any negative y will satisfy before 0. So we only have one constraint. So if we have only one constraint for each of the decision variables, it is always going to be feasible because there are no competing constraints because there is only one constraint. So this is also feasible with respect to y, and this is a feasible LP. And similarly, the other problem that we did was min. 2x plus 10y, x comma y greater than or equals to 0. So again, there are only one constraint for x and one constraint for y. So the question of contradicting each other does not even come here. So this problem is going to be feasible as well. All right, so I hope this was useful. In the next video, I'm going to explain how you can tell a problem is unbounded or not.